Thanks for a nice introduction. I'm Anthony, currently a postdoc funded by this Simon CIQC collaboration at Berkeley. Throughout the year, I've also visited MIT for a few months. This work was done with folks at Simons Institute, very awesome people. Thiago is a strong grad student. He might be somewhere in the audience. And Umesh, of course, you know him. So I guess today in the morning we have already seen some sort of very related topics, and this metastability is something that we want to understand more in this talk. And I have to admit, some of this, even though our goal is more physical, you might secretly borrow some computer science ideas. So please, actually, hopefully that's okay with you. And so to begin with sort of like a motivation. So I draw a square here on the board. Hopefully people can see some of it. So let's take this object, right? This is like a board, some material. If I measure a temperature by a thermometer, it will have the room temperature, right? And then if you look at it, it doesn't seem that it's changing. It will probably stay as is. If nobody do anything with it, it would stay like this for maybe another 10 years, 100 years. So it looks, so it has a temperature, it seems stationary. But do we really believe this thing is like in true equilibrium? Right? So maybe yes, maybe not. And if not, sort of, what is it? Right? So in particular, you can sort of ask the audience, if I redraw this box and I sort of ask you, so how much correlation are there between the inside and outside? Who believe it has area law scaling?
What's the condition? This is...
Oh, like this particular piece. Like this thing.
Oh, this particular piece.
Yeah. Right now, yeah. Yeah, the piece of chalkboard. Who believes it's area law? Who believes it's volume law? Okay, so I don't think there's like it doesn't seem like a definite response, but in either case, it will be interesting to figure out, right? And then that sort of hopefully will motivate what this talk is about. So we try to capture phenomena that looks kind of not changing at fixed temperature, and we try to formalize that, okay? Okay, so, if you believe it's in true thermal equilibrium and you understand this piece of material, this board, you will say, okay, let's take it as a Gibbs state, right? So this thing has appeared a few times in today already. Right? It's very simple to define. Give me a Hamiltonian and give me a temperature, and we actually take inverse temperature. That's a bit easier, so beta. And then this define like a big matrix, right? And in principle, if you have this matrix, you can do everything. You can get lots of physics out of this, right? And then for the purpose of this talk, when I write Hamiltonian, it always means it has few body interaction, and each qubit so interacted by constantly many term, and each term has a unit string. So, for example, think about like a 2D nearest neighbor Ising type model, right? That's sort of the representative. So our proof is actually quite general. Okay? And then, physicists have been working very hard to get a lot of physics out of this. It really captures, it's very expressive, captures lots of interesting phenomena. And so today, the type of thing I will discuss is that if you take a step back and rethink why a lot of this progress is possible, secretly we're using the fact that this object is very structured. Right? Not only we believe this is a good model for thermal phenomena, we also use a lot of structure. So it actually comes out with a pretty big bonus. So for example, for some of you who might care about this area law, so this is one thing that in sort of one very kind of key intuition in understanding low temperature quantum states. And in the thermal context, if you take a Gibbs state, the claim is that if you take a region and then you ask what's the kind of correlation between the interior and the outside, this correlation, if you measure like some kind of number of bits required to describe the correlation in terms of this mutual information, is scaled with the area. Okay, so this shouldn't be like a completely shock. People must have heard this somewhere, but this is sort of the thermal version of the area law. Right? So also this ground state version of area law is like similar, but in terms of just the entanglement. Okay. So far these, if you don't have any of these structures, it seems pretty hard to do any physics of these low temperature states. But then with them, there's actually lots of things you can do, at least in 1D or 2D. But they have been sort of pretty useful. And then today we like to kind of, take a step back and then ask, okay, so if we really use a lot of structure about this gift state, and now if I also tell you that actually things are not, maybe there shouldn't really actually be fully thermal equilibrium, so what are they, right? So what's going on, right? So in the beginning I mentioned this piece of board, but you can think about a lot of things like glass, right? Like molecules or magnets. If you wait long enough, it could be like really, really long time, but eventually something happens, right? Molecules eventually could react after a long time. So, to be sort of very fair, it probably should be more like some kind of energy landscape, and and the thing you see that looks stable, probably just some kind of local minima in one of these wells, right? So this is like a very heuristic figure. I draw it so as if it's all classical, right? But but you can ask, okay, so if I'm going to try to understand these things that looks like local minimas, should there actually be any structure at all, or there just could be like infinitely complicated? Right, so if you want to have like a more dynamical view, right, you want to say, okay, if now equilibrium is not assumed, then if you want to go back to the dynamical view, then it seems that sort of generic dynamical problem with, and someone also don't tell you, people don't tell you what the initial condition is, and it seems kind of very hard to solve, and it just seems it could have lots of possibility, right? It doesn't seem, why there should be any structure at all. Yes, so that is the way we're going to open, so to try to make sense of it, right? But if someone just told you, I have metastable state that could come from very, if I also tell you the dynamics, and I also tell you the initial conditions, in principle, this tell you what the state is, but you might have to solve a full dynamical equation every time someone gives you such a thing. Right, so that would be the guiding intuition, right? That would be, I guess that would be one of the the claim of this talk is that there are actually a lot of structures. Yeah, but a priori, if someone just gives you like a dynamical equation and give you initial state, this is like a very complicated thing, and lots of things could happen. Okay, so here's the main claim. We claim that there, under some model of metastability that I will tell you, we can sort of start building a structure theory of them. So, as the audience says, there actually would be structures, and here are the meta theorem that we show. We show that at any temperature, and independent of how the state become metastable, the claim is that any metastable state always satisfies an area law, an approximate area law, and there's also a closely related property called Markov property. So in the end, it actually comes sort of hand-to-hand together. And so it turns out the claim is that a lot of these area law Markov property that people talk about for gift state actually is sort of not very unique to equilibrium. It actually could hold in sort of a very broad way, and it actually have a dynamical origin. Okay, so that was the claim. And along the way, we actually have to do a bit of work, and then we also have like a toolbox of analytic framework that we develop so to get to these properties that also tell you very different pieces of metastability. Okay. And here, let me sort of have like a disclaimer. So we are working in an open system setting to talk about thermal metastability. And so far, they're sort of, we're not really the only one trying to talk about metastable states. And there have been sort of different versions at just different settings. I don't know how easy it is to really compare them. So one is sort of like a pure state setting closed system, 0 temperature. And the other one is sort of open system but 0 temperature. And it turns out you get sort of quite different. The result you prove actually is somewhat different depending on how you set it up. But here, finite temperature, open system.
There's sort of several meanings to metastability. One, you can think of programmable, for example, as a metastable state. It's a closed, a finite system. And on the other hand, you drew something that has to do with the minimal local versus global minimum. Are you distinguishing between the two? Is this also?
I'll define it. Yeah. Okay, so this is the main theme. So let's start building sort of our formalism. So first, if you want to go out of the equilibrium, one has to define a model, right? So in here, we already have to make a choice of choosing a model. So we just take an open system description. So say like a 2D, imagine like a 2D lattice, and then it's been interacting with a bath, right? So there's going to be two things. One is sort of its own dynamics, so the Hamiltonian dynamics of itself, and also like a system bath interaction. So right, so that would be our fundamental sort of input model. And then here we kind of assume each guy is being constantly interacting with the bath of of some temperature that you know. Okay, so this is sort of what this model, this Lembadian is capturing. Right, well, implicitly we'll assume this is time-independent dynamics. Right, so this equation is fixed. The stages keep evolving, and this is our fundamental model. Okay. And certainly, you can write down any Lembadian, but here we sort of, if you want to study thermalization, if you want to study thermalization and equilibrium states, it better be that the thermal state is a consistent sort of a stationary solution of this. Right, so then, in order to sort of set it up as a dynamical model for thermalization, we kind of make use of a recent constructive family that is sort of convenient, that it can turn any spin flipped into quasi-local and detailed balanced Lembadian. Okay, so detailed balance in the quantum world is like this kind of horrible looking condition. But it's sort of just a quantum version of classical detailed balance. Right? So there's some kind of symmetry between heating and cooling. There's some ratios that you have to obey. Okay, and with this detailed balance, it's a consequence that it always fixes the thermal state. So the thermal state is at least a consistent kind of stationary state of this dynamics. Okay, and to give like an intuition of what this dynamic's doing, it kind of do this weakly. So if you start with like a polyflip, what it does is apply this very weakly, and then apply some coherent reweighting of the transitions to suppress the heating transitions, and then that results in some kind of fuzzy blob of Lembadian that's sort of quasi-local, but it is detail balanced. Okay. So recently there have been sort of quite some work along this direction, in the quantum algorithm community to sort of improve on understanding this type of objects. But for our purposes, this is just like an object that's detail balanced and local, right? And then you can just ask, if this is the model of noise, what can I say? Right? And also, detail balance is sort of not really the only way actually to get consistency with Gibbs states. There's also like a kind of a different direction one can take and think of also non-detailed balanced constructions. Okay, so if we just take this as the our fundamental our open system model, okay, so we just do that, and then we can use that to define metastability. So we're just going to take metastable states to be approximate stationary state of the open system dynamics. Okay, so in this distance, it just means sort of statistical distance of the state. So it means that for any observable you do, it will look like it's not really changing. So if you measure the energy is not going to be changing very much. If you put a local observable, the local observable is not going to be changing very quickly. Right? This epsilon captures how slow it is. Okay. And so let's think about this condition, right? So when I define this, actually, this is a pretty forgetful definition, right? It doesn't care about how the state become metastable. Right? I didn't tell you what is the initial state. I only say, okay, here's the state at this moment, and it's not really changing very quickly. And that's the condition. It didn't care about how the state was made. Yeah.
Is sigma expectation value of observable, or is that an operator? Or
so sigma is the density operator. Yeah, it's the current status of the state. Yeah. We say sigma is metastable if the time derivative is very small.
In this definition, how should
Right now, anything. Yeah. Right now, epsilon can be anything, but usually, epsilon better be pretty small. Otherwise, it's, if epsilon is 1/2, that's sort of not really metastable. So we will want epsilon to be pretty small.
Yeah, to make sure sigma is a many body state.
Yeah, it's a big state. Yeah.
The many body state is not changing.
Yeah.
In any measurable sense.
Yes. Yeah. Exactly.
Are you going to allow for epsilons that are order 1?
Our result will be most interesting is epsilon is small. Yeah, like polynomial small or exponentially small. Yeah.
But I think, right, there's cases where you would want epsilon perhaps to not be independent of system size, like false back to
Right, so that we can, our thing actually requires epsilon to be growing a little bit with with the system size, for just like because there's some entropy bound we have, there's a factor of system size that come in. But it will be interesting if one can get rid of the, yeah.
Okay, so this is not, you need epsilon for that with system size.
In our current result, yes. Yeah, yeah. But this is, right now this definition is just a definition. Epsilon could be anything. Yeah. Okay?
Actually, my actual question was that initially you started with this example in the blackboard.
Yes.
So your condition is demanding for the global state.
Yes.
So now the blackboard example, the blackboard is stationary.
Yeah.
The rest of the universe is evolving. Right? But here
Yeah.
we are demanding the whole thing is not evolving.
Yeah, yeah.
So that's just to make sure that's the situation.
Yeah, but yeah, so we're not asking for local stationarity. This is sort of, the state for any global measurement is not changing. Right? So, yeah.
Maybe a follow-up. So you are now considering the possibility of like the state is evolving, that you could be evolving approximately equals orbit, or is that not possible, like with Metastable?
I mean, if it's like doing this, then the derivative is pretty big, right? Derivative, like it's changing, right? So I'm just saying it's statistically not changing. So any measurement is not able to say it's changing. Yeah.
Think about your current tool, the Metastable, is it a typical view that there is some kind of energy barrier on this such
Right. So this is all just a guiding figure. Like we're not going to use this. It would be interesting to further pursue this. But this is just like how people often talk about it. Right? This is just a figure. So our definition is really stationarity. So this is our starting definition.
You're saying you're also not going to do the exponent of this barrier.
Right. We're not requiring that. Yeah. We just now we just here's the definition. What can you say? Okay. And so here's kind of one cute thing. Right? You might say, oh, it might be really hard to get something to be truly stationary, right? If it's like a global condition. But it turns out there's like a trick to always produce a metastable state. And this is actually something reminiscent of ergodic, like some trick used by von Neumann in ergodic theory. So if you just always do a time averaging of dynamics, it always become sort of slow changing. Yeah. So in some sense, like you can kind of systematically produce these guys. Given any initial state. Right, so epsilon will be inverse t. Yeah. Like if you just, yeah. So epsilon is inverse, scaling inverse with t. Okay. So so this is actually very much motivated by or inspired by some classical work on this related subject. So if you're interested in classical Markov chains, you can look at this paper. Okay, so this is our definition of metastability. So approximate stationarity. And you might think, well, this looks so general. What can you really get out of this, right? But it turns out there's a lot. Okay? So the claim is that only with this assumption that things are not changing, you can get an area law. Right, so if you look at this equation, there's like a first term that looks like sort of the thermal area law. That's exactly the same as that would be for Gibbs state. But then there's some correction at scale with some parameter that I will elaborate. Okay. Okay. So some remarks. So this always, this works for any bounded degree Hamiltonian. So it doesn't require any kind of spatial geometry. It could be 2D, but it could be 3D. it could even on this, could be even on this sort of expander graph. That's sort of all fine, as long as it's like constant degree. And also, our result doesn't actually care about thermal phase transitions. It doesn't require so much of the physics, so this is just true. So yeah, so really the assumption is really just metastable. Like so changing implies area law. Yes.
Your second term has an absolute of A, which is the size of the subregion.
Yeah.
Is it volume of such a system?
Yeah.
So why would you say area law?
So yeah, so here, if epsilon is small enough, then the second term disappears. Yeah, so this is like a local, depends on how metastable it is. The more metastable, I'll discuss this, the quantitative.
The particular result is meaningful when epsilon is exponentially small.
I'll talk about it next slide. Yeah, but there's some, and this is actually also tight, so it's hard to avoid this. Yeah, I'll explore this. Yeah. So any more questions about this current result?
Is that exponentially in A term the space dimension?
Oh, sorry. The number of sites in A.
Oh,
so it's polynomial in the dimension of A. Yeah.
It's not exactly dimension, that's all.
Yeah, more or less. Yeah.
Does it give anything in the case of Oswald interactions?
Constant degree. So if a spin talks to everyone, then it doesn't work.
No, but if a spin talks to just a few, without
like
geometry at all.
Yeah, if it's like a sparse graph, then it also works.
In a standard, does it give something non-trivial?
I mean, it would have this formula, but then you have to plug in the bound, like what is the boundary? Like if it's on expander, the boundary is the same as the volume, then maybe it's it doesn't say too much more. But if it's like expander, but then there's like a little bottleneck, then that would be applied. Yeah. Okay. Yeah. So let's play a little bit about these parameters. So here's epsilon is one of the parameters, right? And then the error term grows exponentially with the number of degree of freedom in the region. So if you do some conversion, you would say, oh, look, if epsilon, for any epsilon I have, you can get like a log size region. And you might say, oh, this looks not very useful. But actually, I would say this is really like a worst case bound, because our result doesn't care about the physics of the model. This is just, it should handle even cases where things are very glassy. Okay? So this is like a worst case bound. And in fact, this is actually, it's actually tight. We'll show an example that is more or less tight. Okay? So how small could this epsilon be? And actually, if you have a physical model, right? It's for example, in this 2D or 4D, a 2D using model of 4D toric epsilon could actually be exponential with the free energy barrier, and we expect this to scale with the length of the system. Okay? So this could actually be very big, right? So our result, even though it has the e to the system size, e of the subregion size, it actually still means something, macroscopic. Okay? And it depends really on the system. If the system is sort of fast mixing, then when epsilon is very small, it just means that you're already at a Gibbs state, right? So our result is sort of most interesting when your system have like a large energy barrier, so that epsilon could be very small, but not a Gibbs state, right? And then they would say all these states actually deep inside these potential wells are sort of very actually have area law in a very strong sense.
You say all these states, it's the metastable state.
Yeah, sorry. Yeah, all the metastable state. Yeah. Okay. So this is the example I was mentioning. So if you just take like a try to configure like a hard disk, then you can by assembling a bunch of Ising models and using like a small size region to store like 1 bit, then you can almost get a volume law. Right? In some sense, that's why you can store information like almost volume law in real life, right? So if you play around the parameter, then by having like two copies of hard disk of exactly the same information sitting next to each other, you could have a volume law of correlation, almost volume law, but then it's also exponentially metastable. Okay, so this sort of matches up to polynomials are sort of this e to the a scaling we have. Okay. So that's the result, and let me try to get into some of the ideas behind this. So one can ask, where do these area law come from? And they actually could come from very different origins. So in a classical world, people never talk about area laws. Instead, they talk about something even more fundamental, which is Markov property. If you fix a set of spins, then if it's a Gibbs state, then all the data is encoded sort of on a boundary because they have conditional independence. And so then people in classical world don't talk about area laws. Right? They talk about this Markov property instead. And then if you want to prove thermal area law for quantum Gibbs states, it ends up taking a very different strategy. So if this is like a very old, very elegant paper. So they get area law from like a minimization of free energy argument. So kind of very different type of origin of area laws. And then our arguments actually need to combine both. One, we need to first prove like a version of local Markov property for metastable state. And then we'll argue that it just, it actually implies some rigorous version of local minima of free energy. And this somehow fits into the framework of the thermal area law. And that leads to the advertised result. Okay, so in other words, our proof of area law reduces to this Markov property. So the claim is that for any metastable state with sufficiently good metastability epsilon, it has this following kind of recovery property. If I punch a hole by erasing some set of qubits, then there exists a quasi-local detailed balance recovery map that would fix it. Okay, so this is like a recovery type of statement, almost like error correction. And this sort of is an extension of a recent result I did with Kambi's for the actual Gibbs state. So Gibbs state also have this property. Okay. Yeah, so here tau A just means the maximum mixed state. So you really remove this part of the system and replace with some trash on there. And the claim is that there is like a map that would sort of fix it by acting almost locally. Okay, and then this map actually has a very physical origin. So it actually corresponds to sort of turning on the heat locally. Okay, so if there's a region that you want to fix, it has errors, then what you do is to turn on this Lindbladian locally, but only sort of on this region. And then you're going to run for a random time. So there's this, and then that defines your resampling kind of your recovery map. Okay. So in some sense, reheating sort of fix the errors. So that's a pretty nice feature about this thermalizing map. But then if you kind of compare these two pictures, right, recall we want to prove an area law. But then when I present this Markov property, and if you look at just like the size of this, actually Markov property doesn't seem very useful because the buffer zone actually is very, very large. Okay, so this is just a feature of our proof. We end up need to have a buffer zone that scales with the size of A. And that somehow seems kind of different from the picture of area law, which seems that correlation are somehow should just be kind of localized, right? And recall classically, right? This length would just be strictly near, it would be strictly kind of one step away from the boundary, right? So this is really a quantum effect. Okay, so it turns out the remedy of this is to revisit this old paper that proves thermal area law, and go through sort of this minimization picture of the Gibbs state. Right, so recall that free energy is the bound, it's a sum over energy minus temperature times entropy. And then a very beautiful equation that I wrote down in the original proof of area law is that if you compare the difference, right, if you look at the difference of the free energy of the state versus its erasure, then you can reorganize the entropic term and the energetic term. And then, and then you expose this neutral information and as well as the energy difference. Okay. And then the proof of thermal area law just follows by the observation that Gibbs state minimizes free energy. So this thing must be negative. And just by rearranging the equation, you get that the entropy must be bounded by the energy. Okay. So in a proof, the way to make it work for our case is to realize that all you need to know is that is a way to compare these two free energies. And in some sense, it's really only requiring a local minima condition. Right? As long as you have a way to compare these two, the free energy of these two different states, you can get area laws. Okay? And then to tie these ideas together, the claim is that local Markov property is really saying that your state is a local minima of free energy against erasure. Right? So again, we draw this bottom well picture. So imagine your state is in one of these wells, and then someone apply a local erasure. So then it excites something within the well. But then you apply your recovery method, it somehow fixes the state. And there might be like a little leakage. And then the way to go now is to realize that the only way for this to happen, for the state to have Markov property, and then both, to have Markov property, is that the erasure must have raised the free energy. And this is because the recovery map you picked actually monotonically decreased the free energy because it's detail balanced. So once this equation is sort of looks very, very simple. Once you put the piece together in the right place, it's really just saying that Markov property is the same as local minima of free energy, and that immediately implies an area law. Okay, so actually the most of the technical part of the paper is to actually prove this local Markov property, and that requires us to develop a lot more technical tool to get this. And so roughly the conceptual question is really just, if you excite a metastable state and you run some dynamics, why does it have to return to the same metastable state? So that is sort of the underlying conceptual question of proving this local Markov property. And that ends up requiring develop a lot of extra framework to actually prove this local Markov property. And I guess I'll just show you some cool equation that I really like. So it turns out this quantity plays a very important role. So instead of thinking about just the stationarity of the state, we consider this particular function, which is the free energy. We just directly consider the rate where the free energy is changing. And turns out this is like a very nice and crazy looking expression that you can trace all the way back to classical diffusion. So there's like some, people call this like a de Bruijn's identity. And you can look at this, like you can, this is, in the classical case, this is like the KL divergence. And is related to some kind of gradient of log likelihood ratio. And we end up getting some crazy thing that's sort of the non-commutative version of this Fisher information. Okay. So the claim is that whenever your metastable state is metastable, it also is the same as this Fisher information is being small. And this actually gives a lot of leverage in try to understand the state. Okay. And this log might look kind of crazy, right? This log sigma looks kind of like a thing that you never want to touch. But then we're able to further massage it into a slightly more physical version of this. It ends up boils down to the following identity. So if you have a metastable state, you take the square roots and you apply an operator on the right. The claim is that it's actually the same as applying the A on the left-hand side, as long as you conjugate with the Gibbs state. Okay. So this turns out being a very, very important part of the proof. This allows you to basically pass A freely with local operator. To pass the metastable state freely with the local operator. And that,
so just to confirm, rho here is the true equilibrium?
Yes. And if you observe, if you put rho here, this is just equal. But the claim is that if you take a square root of a metastable state, it's also true.
Do I need to worry at all if rho is like a symmetry breaking state? Because the rho to the minus half might blow up.
Right, so you're exactly right. So in the actual thing we do is some filtered version of the local operator. You don't take the exactly local operator, you have to cut some high energy contribution. And once you cut that, you get this works. Yeah. So that's actually the reason why this is not trivial is because of that divergence. So we do have to handle that.
But this is equal up to what?
Right, so this thing will be, the quality of the approximation will be controlled by epsilon. Yeah, if it's very, very metastable, then there's a sense, I guess, exactly in this expression that this thing has to be very small. If it's exactly zero, Gibbs state have this probability that it's exactly zero. Okay, and anyway, after lots of work, you can show that the Fisher information bounds this quality. We prove that. And for those of you who might, who are familiar with like sort of this infinite system size limit, so this condition is actually very close to this so-called Kubo-Martin-Schwinger KMS condition in StatMech. So it's actually quite interesting to see how much more you can squeeze out of that. Okay, so I'm near the end of the talk. So just want to put some very broad discussion. So this is by no means trying to be rigorous, but this is just one theme, about whether metastable state could be something we want to look for in quantum simulation. So the broad question is that usually when we talk about dynamical simulation, it seems sort of feasible, but many times so it seems very general. And at the same time, if you look at equilibrium simulation, sometimes it feels it's very well defined, specific, but often very hard to prove things exactly. But then, so metastable state somehow suggests that it might be something that is very concrete, but then lies somewhere in between. So we're not trying to push, try to make this even so much more concrete, but this is also some food for discussion. And then there's some very natural questions for this crowd here. I know people here, some of the people here really like bottlenecks, so it would be cool if one can squeeze out a bottleneck out of this, our formalism. We currently don't have that. And then one can ask, is there a way to classify metastable states, right? If you just write down L sigma is very small, could one have like a simple classification of them? And then, I know people here also really love quantum memory, so, maybe you have some comments here. So I'll just stop here, and thank you.
You have a question, Andy, or other questions?
Maybe, so for this part on sort of an approximate KMS condition, does that go wrong if epsilon is independent of n? Or is that just the area law? Like, is this meaningful if epsilon is constant?
So we are thinking about that. Yeah.
Okay.
So, yeah.
Because I guess just a sort of small comment is I think
it's not clear to me whether metastability should, if epsilon is vanishing in the thermodynamic limit, maybe that's just exact stability. It sort of depends on the order of limits that you take.
Yeah, exactly. Yeah. So here we're in a sort of computer science setting where n is finite, and epsilon could be poly n, exponentially n. Yeah. So we're not able, we currently don't have like a thermodynamic statement.
Okay, thank you. Maybe you already answered this, but somehow it didn't come to me clearly. So because we are demanding epsilon to be the rate of change for the global state, the rate of change for any local subsystem will be smaller, or at most epsilon. So if you want to show, say, area law for subsystem A and A bar, you could just choose B, which covers a larger area that includes A and A bar and their boundaries, and they just trivially bound using area law of the thermal states, and then put an epsilon there. So I was wondering, what was wrong in this naive argument, and why did you have to go through these more advanced approaches?
Oh, okay. So I think that the issue here is about boundary conditions. Yeah. So if you want to perfectly cut a part of the system, it's still kind of, some boundary term actually still goes out.
Yeah, but for example, say 2D, so geometrically easy to see. Okay, so you have A and area law coming from the boundary part. Just choose B to be say several factors larger, that covers sufficiently large of including A and A boundaries, right? So that's not enough. Those kind of reasoning is not enough.
I mean, in some sense, this is what happens. In some sense, what this Markov property is doing. It does say that if you take a big enough radius, you can do this recovery.
Yeah.
But what is not obvious from existing, area law is that the proof always assume have the global Gibbs state, right? And now if you want to capture a version of local, local Gibbs state, then in some sense this is what we're doing. I don't know if that.
I see. Okay.
Yeah, because you can have something that's strictly local stationary on this patch, but then it didn't tell me what's the boundary condition on outside.
Okay. Does that mean that if suppose I give you extra conditions, say locality of temperature, so that it's not only globally Gibbs state, any subsystems up to the boundary buffer is still Gibbs state? If the system satisfies their properties, then your proof will be very easier.
Oh, I mean, if you already assume local marginals are Gibbs, then I believe you can almost get it for free.
Okay, thank you.
Since you talked about this local recoverability procedure and that you can locally heat without going through this free energy barrier, does this also allow you to prove this fast mixing within a logical sector that Tiago was trying to prove?
So that certainly requires, first, I think that is not always true. So that certainly requires extra inputs. And then in some sense, I didn't show you, but it has to do with how long you're going to have to run this recovery map. So we have some kind of generic bound that's scale e to the a. So that's actually where it comes from. You can think of it as some kind of local mixing time. So we want our result to work even for spin glasses. So, you have to run this local recovery map for a very, very long time.
No, not if you're only trying to prepare a local minima state. Even in a spin glass, if you're just trying to prepare a local minima, a metastable state, you don't have to run it for very long. Or intuitively, you don't have to run it for very long.
In our bounds, we can handle all the cases, and there are cases where this is tight. But I do agree that in many physical systems, you should just quickly convert to some fixed things. I agree, yeah. In many physical systems, that's the expectation.
Yeah, we can take one more. Why not? Unless there are objections.
Thanks for the nice talk. So you talked about that you want to achieve a structure, kind of characterization of the structure of metastable states. So now this was all about, I guess, the structure of a single metastable state. Can you get anything out of this about the set of metastable state? Is it convex and stuff like that?
In some sense, the condition itself is convex, one norm, L sigma, the one norm is convex. So in some sense, the stationary state is convex. But I don't know how much you can get out of the thing we have proven, right? Because our thing is for any metastable state, this is already true. So the whole set actually already have this property. Yeah.
Okay,
yeah.
Thanks.
You mentioned this result that you have this kind of local minimum condition with respect to erasure Do you think that there is some stronger version of that that's true? That like your local minimum with respect to like any local channel?
Oh, so here is, so certainly it is true if you replace with any state. I believe it's also true. Yeah, so I think if I remember, I think the proof also goes through for any local channel, any CPTP map. So it has to be trace preserving. Yeah.
Okay, let's thank Anthony again.